So let's take a look at example 6. So in this problem, we notice that we are trying to write the summation notation for 2 plus 4 plus 6 plus 8 plus 10. Okay, so notice we have 5 terms. Okay, so we could easily write a summation going up to 5. We could start it at 1. And now because we're counting by 2's, we could say that this would be 2i. Okay, so this would be it. So just as a check, this would be starting I at 1. This would be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. Okay, so notice that all of these would give us, this will give us 2, gives us 4, 6, 8, and 10. Okay, write summation notation for g of x1 times delta x plus g of x2 times delta x plus dot 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 all the way up to g of x19 delta x. Okay, so that should be straightforward. So we could say this is summation. I notice it's starting at 1 and it's ending at 19. So we have I equals 1 going up to 19. And then we have g of x I and then delta x. And then that would be it. Alright, let's take a look at this one now. Now it says express without using summation notation. So we're trying to figure out what is this thing, right? Okay, so let's figure that out. So starting at I is equal to 1. So that means we have 3 to the first. Next will be 3 to the second plus 3 to the third plus last one will be the fourth, so 3 to the fourth. Okay, so we could evaluate each of these. Well, 3 to the first is 3. 3 squared is 9. 3 to the third is 27. And 3 to the fourth is 81. So plus 81. And we could add that all together, and it gives us 120. Okay, express the sum of the product of h of xi delta x from I equals 1 to 30 without summation notation. Okay, so that basically tells us we have h of x1 delta x plus h of x2 delta x. And I'm not going to write all of these. I'm going to use the trick they did earlier up here with the 3 dots. That's what I'm going to do here. So plus dot 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 plus, and then we write the last one, h of x30 delta x, and that would be it. So those 3 dots save us a lot of work with all the terms. So that implies all the terms in between. Okay. Let's take a look at this next one. So we're going to do this problem. Let's consider the graph of f of x equals 600x minus x squared over the interval 0 to 600. Approximate the area by dividing the interval into 6 subintervals. And then the next part would be approximate the area by dividing this interval into 12 subintervals. Okay, so first we're going to do this by dividing the interval into 6 subintervals. So that first part we'll figure out delta x. Right, so delta x would be done by taking b minus a over n. So our b minus a is going to be 600 minus 0, and then n is the number of intervals, so 600 over 6. So each subinterval is 100 wide. Okay, so starting at 0, we go every 100. So we have 100, 200, 300, 400, 500. Okay. So what we want to find out is, we're going to do this formula to figure out the area of the 6 subintervals. Okay. So we're going to figure out, we figured out delta x, so each of the delta x is 100. So that's the width. And then we're going to figure out the height of each subinterval. Okay, so when we look at the first one, the first height is 0. Right? Then the next height will be what happens when we plug 100 into the function. So we're going to plug into our function. Okay, so let me make a table. That might make it a little easier for us. So x is going to be 0, 100, 200, 300, 400, and 500. Okay, so take each of these values, plug it into the function we had. Okay, I plugged these in ahead of time. So when you plug in 0, that's easy, we get 0. When you plug in 100, you end up with 50,000. When you plug in 200, you end up with 80,000. When you plug in 300, you get 90,000. When you plug in 400, you get 80,000. And then when you plug in 500, you get 50,000. Okay, so we're going to be doing each of these values we got on the right under y, we're going to be multiplying by 100. Okay, so we have 0 times 100 plus 50,000 times 100 plus 80,000 times 100. I'll continue down here. 90,000 times 100 plus 80,000 times 100 plus 50,000 times 100. Okay, add up all these together. and you'll get 35 million. Okay, so now let's come up with hopefully a better estimate. We're going to use 12 subintervals. Okay, so we're going to take the same function, f of x equals 600x minus x squared, divide into 12 subintervals. Okay, and we see, and you see we have the 12 subintervals now. So if it's 12 subintervals, 600, if we get delta x, 600 minus 0 over 12, 600 over 12, so that gives us 50. So the width of each one is going to be 50. 50, 0 to 50, and then 50 to 100. And then in between will be 150. Okay, so notice how our f of 0, then we have f of 50, f of 100, f of 150, and we're multiplying these all by 50. Okay, so let's make a table of values. So we'll have, starting at 0, 50, we keep going up by 50 because that's the width of each interval. 150, 200, 250, 300, 350, 400, 450, 500, 550. Okay, so that's 12 of them. Okay, so now we're going to take each of these x values and we will plug into our function 600x minus x squared. Okay, so I did these ahead of time. So for 0 is 0, 50 is 27,500, 100 is 50,000, 150 is 67,500, 200 is 80,000, 250 is 87,500, 300 is 90,000, 350 is 87,500, 400 is 80,000, 450 is 67,500, 500 is 50,000, and 550 is 27,500. Okay, so now we're going to take each of these y values and multiply by 50, add them up, and that should give us our approximate area. Okay, so we have 0 times 50 is 7,500 times 50 plus 50,000 times 50 plus 67,500 times 50. Continue down here, plus 80,000 times 50 plus 87,500 times 50 plus 90,000 times 50 plus 87,500 times 50 plus 80,000 times 50. $67,500 times 50 plus 50,000 times 50 plus 27,500 times 50. Alright, multiply these all up, add them all together, and we end up with 35,750,000. Okay, so the moral of the story, the more subintervals, the more rectangles, if you will, the better the approximation. Okay, so looking back at the previous part, with only 6 subintervals, we had 35 million. With 12 subintervals, we had 35,750,000. Okay, so let's take a look at section 4.3, area and definite integrals. Okay, so to find the area underneath the curve, what we do is we take the integral, right, we're going to integrate it, and then we're going to evaluate the bound. Okay, so we have interval from b to a. So if we have the integral, we're going to plug in b, and then we're going to take away the area of the integral with a. So if you will, if a is represented by this region, and we take that away, we will be left with the area between b and a underneath the curve. Okay. The way we do this is we integrate the curve, and then we plug in the bounds. Right? We plug in f of b, and we take away f of a, and the result is the area under the graph over the interval a to b. Okay, so this is important. Okay, so let's do example 1. It says find the area under the graph of f of x. Okay, so we're going to integrate over the interval 2 to 5. Okay, so that means we will be going from we're going to integrate it. Okay, and I'll introduce this part to you guys. When you see the integration, you'll see the 2 and the 5 here. That'll tell you that it's going from 2 to 5. Okay, and we put our function in here in the integrand. So 1/5 x squared plus 3 So one thing we do when we do this is a definite integral now, so it's between, if you want to look at the graph, our graph is here on the right, so we're going to find the area underneath the curve from 5 to 2. Okay, so we'll first integrate it. That means we'll have 1/5 x cubed over 3 plus 3x. And when we do a definite integral, we no longer have the c. Right? C, for simplicity's sake, we set c equal to 0. So there's no more c. Okay. Okay, so to simplify this, let me rewrite the 1/5 here. So this is really 1/15 x cubed plus 3x. And this is what we would do with the 5 and the 2. We would put the 5 here and the 2 here. And this will tell us to evaluate. Right, so if you're doing this in terms of like a function notation, this is basically what we want to do. Plug in 5 into the new function, and then plug in 2, and then we subtract. And that gives us the area underneath the curve. Okay. So for the first one, we have 1/15 of 5 cubed plus 3 times 5 minus, plug in 2, 1/15 of 2 cubed plus 3 times 2. Okay, so doing this gives us 5 cubed is 125, so 125 over 15 plus 15. 2 cubed is 8, so that's 8 over 15 plus 6. And then we evaluate this, and this should end up giving us 16 and 4/5. Okay. Let's take a look at this next one. Find the area under the graph of y equals x squared plus 1 over the interval -1 to 2. Okay, so that means for this one we would go integral x squared plus 1 Okay, so when we integrate it, we would have 1/3 x cubed plus x. Okay, so basically we're going to plug in 2, we're going to plug in -1, and then we're going to subtract. Okay, so plug in 2, so we'd have 1/3 times 2 cubed plus 2 minus 1/3 -1 cubed plus -1. Okay, so that gives us 2 cubed is 8, so 8/3 plus 2, and then here -1 cubed would be -1, so we have -1/3 minus 1. We have 8/3 plus 2. Minus of a minus is plus 1/3. Minus of a minus is plus 1. So that gives us 9/3 is 3. 3 plus 3 is 6. So a total of 6. So let's take a look at the next one. Let y equals x cubed represent the number of kilowatts generated by a new power plant each day, x days after going online. Find the area under the graph of y equals x cubed over the interval 0 to 5 and interpret the significance of the area. Okay, so basically we're doing this. And the function is x cubed. Okay, so we would integrate this. This would be 1/4 x to the 4th. So now we're going to plug in 5, we'll plug in 0, we subtract. let's see what we get. 1/4 of 5 to the 4th minus 1/4 of 0 to the 4th. Well, 5 to the 4th is how much? 625. So we have 625 times 1/4 is that. Well, 0 to the 4th is 0, so this is 0. Okay, so your final answer is 625 divided by 4 would be about 156 and 1/4. So this area under the curve, this represents the total number of kilowatts generated during the first 5 days. Okay, so total number of kilowatts generated during the first 5 days. Okay, evaluate this integral, so in more abstract terms. Okay, same thing as usual. If we integrate x squared, that would be x cubed over 3. So in other words, 1/3 x cubed. And it's from b to a, so put b here, a there. So that means we would have 1/3 of b cubed minus 1/3 of a cubed. And you could say this is b cubed over 3 minus a cubed over 3. Okay, evaluate each of the following. So here in the first one, they give us, let's integrate this. We have x cubed over 3 minus x squared over 2. Okay, so that means we plug in the 4, so we would have 4 cubed over 3 minus 4 squared over 2 minus -1 cubed over 3 minus -1 squared over 2. Okay, so that gives us 64 over 3 minus 16 over 2 minus -1 over 3 minus 1 over 2. Okay, so it gives us 64 over 3 minus 8, if we distribute the minus into the parentheses, plus 1/3 and plus 1/2. And if we put all that together, we would end up with 14 and 1/6. Let's take a look at B. This was A. B. If I integrate e to the x, I end up with e to the x. Now I evaluate from 3 to 0. So I'll have e to the 3 minus e to the 0, which gives me e to the 3 minus 1. And then that would be it. We could leave it like that. Okay, C. Integrating here, we're going from e to 1. So if we integrate the 1, we get x. Integrating 2x, we get x squared minus, Integrating 1 over x, I recognize that. That's ln of x. And we'll go from e to 1. Okay, so first we plug in e. So we have e plus e squared minus ln of e minus 1 plus 1 squared minus ln of 1. Alright, well, we have a couple things going on here. We got ln of e, which we should recognize. ln of e is equal to 1. And then back on the back end, we have ln of 1. ln of 1 is 0. Okay, so we got e plus e squared minus 1. And then in here we got, if I distribute the minus, that's minus 1 minus 1 squared is 1. And then we got the 0, so that doesn't count for anything. So that would be it. So we just end up with e plus e squared, and then negative 1 minus 1 is negative 3. Okay. Let's take a look at our next scenario. So we look at our next example. F of x equals x squared minus 1 over the interval 0 to 2. So notice part of the graph dips below the x-axis. Okay, so what happens when we go below the x-axis? Any region that's below the x-axis is actually a negative. We don't want to say it's a negative area, but the area of that region turns out to be negative. Any region that's above the x-axis has a positive area. Okay, so there's a couple ways to do this problem. The first way I'm going to show you guys is we're going to break this up into two integrals. We're going to go from 2 to 1, and then we'll go from 1 to 0. Okay, so I'll have 2 to 1 integral of x squared minus 1. And add to it, I'll do from 1 to 0 of x squared minus 1. Alright, so when we integrate x squared minus 1, we end up with 1/3 x cubed minus x. X cubed minus x. Okay, so we plug in the 2, so I'll figure this one out over here. So we got 1/3 of 2 cubed minus 2 minus 1/3 of 1 cubed minus 1. Okay, so that means I have here, this is 8, so 8/3 minus 2. 1 times 1/3, so it's minus 1/3. Minus and minus is plus. So that part gives me this part gives me 4/3. Let's take a look at the part that's under the x-axis from 1 to 0. So I have 1/3 of 1 cubed minus 1 minus 1/3 of 0 cubed minus 0. So this gives me 1/3 times 1 minus 1. And then this piece would be 0, right? 0 cubed is 0, 0 is 0. So this is just 0. So 1/3 minus 1 would be negative 2/3. And then I'll add together the two. I have 4/3 plus negative 2/3, which gives me a total of 2/3. Okay, now let me show you the same problem. You can do it in one shot. It goes from 2 to 0, right? And x squared minus 1. So when we take the integral, we get 1/3 x cubed minus x from 2 to 0. Okay, so plug in the 2. So 1/3 of 2 cubed minus 2 minus 1/3 of 0 cubed minus 0. So that gives me 8/8 minus 2 minus, and this is 0. So here I have 8/3 minus 6/3, which is just 2/3. Okay, so it gives you the same result either way. Notice what it's doing though, as you do this, it's going to give you the net result, if you will. Okay, so notice the positive piece to this had 4/3 as an area. The negative piece had negative 2/3. And then what happened? We added them together, and then whatever was left was that's kind of like your combination of the positive with the negative. Okay, so we have a 2/3 net result. Okay, same thing here. We end up with the same result. Okay. Let's take a look at this next example. Looking at the graph, we have this function negative x cubed plus 3x minus 1, and we're going from 2 to negative 1. Okay, so just looking at it, initial thoughts, we see there's a lot more negative area, a lot more negative real estate, if you will. So if we evaluate the integral from 2 to negative 1, we should expect, if we're predicting the sign here, we should expect a negative result, because there's a lot more negative. This negative will offset with the positive, but there'll be a lot more negative here, so we should expect a negative end result. Okay. Alright, so let's integrate it. So when we integrate this, what do we have? We have negative will be 1/4 x to the 4th plus 3/2 x squared minus x Okay, so first we plug in the 2. So negative 1/4 2 to the 4th plus 3/2 2 squared minus 2 minus negative 1/4 negative 1 to the 4th plus 3/2 negative 1 squared minus negative 1. Okay, so this gives us 2 to the 4th is 16. Negative 1/4 of 16 would be negative 4 plus 2 squared is 4. 4 times 3/2 is 6. And then here, negative 1 to the 4th is 1, so we have negative 1 to the 4, negative 1/4 plus negative 1 squared is 1, 3/2 plus 1. Okay, so here we have negative 4 and negative 2, negative 6 plus 6, so this is 0. And so here we end up with, this would be 1/4 minus 3/2 minus 1. Okay, so this ends up giving us negative 2 and 1/4. And just like we predicted, a negative overall value. Okay, so that's the end of our lesson for 4.3. Okay, go over this. Any questions you have, just write me an email or bring it up when we meet in class tomorrow or later today. Okay, have a good day, have a good night. See you soon.